Hello everyone, my name is Anushri, third year BE in Information Science and Engineering student at Sri Venkateshwara College of Engineering, Bengaluru. Today's topic of my presentation is CRC and error correction mechanisms. So what are errors in networking? The error simply means any flaw or deviation that occurs while the information is transmitted from the source to destination in a computer network. In other words, if the message or data transmitted by the source is not identical to the one received at a destination, we can say that there is some error in the computer network. In a network, the data or a message is transferred in the form of bits that follow a specific sequence. If there is any deviation or a flaw in the bit sequence, then there is an error. Now let's understand the type of errors that can occur in a computer network. Single bit error. This error occurs when the single bit, that is single binary data or a digit in the message is flipped during the transmission and the received message at the destination side differs from the original message by single bit. For example, if a single bit, that is 1 in the source message, is flipped to 0 or a 0 is flipped to 1, we can say that there is a single bit error in the transmission, which is shown below. Here, the sender has sent the message 0 but which has changed to 1 at the receiver's side. Multiple bit error. This occurs when there is a deviation in a multiple bits of message during its transfer from source to destination. The bits that are flipped need not be continuous sequence of bits. Thus, a multiple bit error is found when any non-continuous sequence of bits is flipped in a transmitted message. The example of this error is illustrated below. Here, 10 has been converted to 01. Burst error. Burst error is similar to multiple bit error, but the error occurs in a continuous sequence of bits. Multiple bit error with just one difference, that the bits that are flipped follow a continuous sequence in that bit representation. This occurs when physical damage to a disk, which causes a change in the consecutive bit sequence of the source message happens. An example of this burst error is demonstrated below. 00100 has been changed to 11011 in the receiver's side. So one of the mechanisms for error correction is Hamming codes. Hamming codes provide another method for error correction. Error bits called Hamming bits are inserted into the message bits at random locations. It is believed that the randomness of these locations reduces the odds that these Hamming bits themselves would be in error. This is based on a mathematical assumption that because there are so many more message bits compared with the Hamming bits, there is a greater chance for a message bits to be in error than for a Hamming bit to be in wrong. Determining the placement and the binary value of a Hamming bit can be implemented using hardware, but it is more often to implement than using the software. The number of bits in a message, that is M, are counted and used to solve the following equation to determine the number of Hamming bits. Using the equation, 2h must be greater than m plus h plus 1, where m is number of bits in the transmitted data. Once the number of Hamming bits is determined, the actual placement of these bits into the message is performed. The bits are incorporated using the right-hand side, from the right-hand side. It is important to note that despite the random nature of these Hamming bit placements, the sample placements must be known and must be used by both transmitter and the receiver. Once the Hamming bits are inserted into their positions, the numerical values of these bit positions of the logic 1 bits in the original message are listed. The equivalent binary numbers of these values are added in the same manner as used in the previous error methods by discarding all the carry results. The sum produced is used as the state of Hamming bits in the message. The numerical difference between the Hamming values transmitted and that produced at the receiver indicates the bit position that contains a bad bit, which is then inverted to correct it. Example, let's understand this with an example. The given data, it will be 100,000 10101, that is 14 bits. The number of Hamming codes must be 2h must be greater than m plus h plus 1. H, we need to determine h, and m is the number of bits in the data transmitted from the source to destination. To satisfy this equation, h must be equal to 1. So 5 Hamming bits should be incorporated into the data from the right hand side. So we will incorporate the 5 Hamming codes from the right hand side, at the alternate positions. So now the count the position where binary ones are present. Wherever we find the one, we actually obtain that binary placement number. So adding use mod 2 operation, that is XOR operation, the result will give the Hamming code at the transmitter end. So here we can see we have the one at second position and sixth position, 11th position, 12th position, 16th position, and 19th positions. So we write down the binary equivalent of these decimal numbers, and we apply the XOR operation of these numbers and calculate the Hamming code, which we will obtain 00000. This Hamming code will be incorporated at the places of H in the data bits, and the data will be transmitted. So instead of this H in this second position, sixth position, ninth position, 12th position, we'll change this H into the 0 and we'll send the data. So how to find out there is an error in the data? The data has been transmitted from the sender to the receiver, from source to destination. But how to find out if the data is wrong or if it is an error in the data? So let the receiver receive the 12th bit position as a 0 instead of 1. The receiver also finds out that Hamming code in the Hamming code as the same way as the transmitter using the XOR operation. So here we had the 12th bit as 1. So we calculated the XOR operation of 12th bit, including the 12th bit, we have calculated the XOR operation and Hamming code as 00000. But here the 12th bit has been changed to 0. So we'll not include that into the binary equivalent numbers. So we'll calculate only 2, 6, 11, 16, 19 XOR operation, and we'll calculate the Hamming code at the receiver side. That is 01100. We'll get this Hamming code, but instead of 00000, we'll get 01100. But this is equivalent to the missing bit, that is 12th bit. The binary equivalent of 12 is 01100, as you can see in the slide. So here we have calculated the same 01100. This is the bit which has been which has occurred an error and it has been misplaced. So Hamming code at the transmitter side was 5 zeros, but the Hamming code at the receiver side is 01100. That is binary equivalent of 12. The decimal equivalent for a binary is 12, so the error is occurred at the 12th place. So by this way, we can determine the error and we can correct the error. So let's understand the Java code for CRC. So first we'll import java.io.star, that has the collection of packages, and we'll create a class CRC. And we have the buffer reader, that is a buffer for storing the data bits from the user. We initialize the arrays using data, divisor, and reminder, CRC, and dividend. So we also declare the data bits, divisor bits, and total length. Then we ask the user to enter the number of data bits. So user will enter the number of data bits, and then we'll ask the user to enter the data bits, that is in the form of a binary number, that is 1 and 0. And then we'll ask the user to enter the number of bits in the divisor. Then we'll enter the divisor bits from the user, and using this we'll calculate the CRC. For CRC, we will append the number of zeros, that is if n is equals to 3, then we'll append n minus 1, that is 2 zeros to the CRC bit that we have been received from the user. So after this appending, we'll calculate the remainder using the divisor and the CRC bit. The remainder can be calculated using the function, as you can see here. Remainder is equals to divide, divisor, and remainder and div. So using this, we can calculate the CRC. CRC is actually calculated using the XOR operation. So we'll calculate the XOR operation and we'll determine the CRC. For this XOR operation, we'll apply the XOR operation between the divisor and the remainder, and we'll calculate the CRC bits, and then we'll print the CRC code to the user, and then we'll ask the CRC code to be obtained from the user, that is at the receiver side. We'll ask the user to enter the CRC code that has been displayed previously. So then the user will enter the CRC code of total length bits, and then we'll check the remainder for the CRC bit. If the remainder is same as the receiver side, as the sender side, then we'll say that if it is not equal, then we'll say that there is an error. If it is equal, then there is no error. So So if the reminder is not equal to 0, then we'll print there is an error during the transmission. If the reminder is equal to 0, then we'll print no error. So while true, then we'll perform the operation, that is reminder the current plus I, that is reminder and the divisor. We will actually perform the XOR operation once again at the receiver side to check whether the number of bits that are being transmitted from the sender to the receiver are same, and the bits actually are same using the reminder. If the reminder is 0, then we'll say that there is no error has been not occurred. If the reminder is not 0, then we'll say that error has been occurred during the transmission. So the output will be enter the number of data bits, then the user will enter 8, then they enter the data bits, that is 10110011, and then we'll collect the enter the number of bits in divisor, that is 3, and then enter the divisor bits, that is 101, and the output will be CRC code that will be calculated using the XOR operation between divisor bits and the reminder. So then enter the CRC code of the 10 bits, that is appending the zeros that has been provided above previously by the output. So then we'll enter that. If it is same, if the reminder is 0, if as we also checked here, the reminder is not equal to 0, then it is error. If the reminder is same, then it is no error. So here we have entered the same CRC bit, then there is no error. If the CRC bit entered is changed, either 1 is changed to 0 or 0 is changed to 1, either multiple bits or single bit error has been occurred, it will say error. So here no error has been occurred. Thank you. That's all for this video.